This video will deal with the learning target. I can break complete equations into net ionic equations. So it's a continuation off of a single displacement reaction or a double displacement reaction, but basically they're reactions that happen in water. So what is a net ionic equation? Well, a lot of times in chemistry, we're dealing with chemical reactions that happen in solution, right, in water. And when that happens, your ionic compounds are not actually bonded in a compound, right? They're ions in solution instead. So what you can actually do with a net ionic equation is determine which ions actually underwent a change and which ions just stayed in solution. And for the ions that just stayed in solution, you don't really have to report them because they didn't undergo a chemical change. And if they don't undergo a chemical change, then they don't have to be shown in your overall net ionic equation. So the normal chemical equations we show with the double displacement reactions shows your ionic compounds. But in reality, all those ions are dissolved in solution. A net ionic equation reports to you only the ions that underwent the chemical change. It doesn't tell you about every ion in solution. It only tells you about the ones that changed. So on the screen here, you can see the progression of how you go from a complete equation, which is a normal equation like you've done for double displacement reactions, and in the end, you convert it into something called a net ionic equation. Now, the difference between the first one and the last one, you can see, is that there's no potassium and there's no nitrate reported in the end because those two ions didn't undergo a chemical change in the end. And the way you determine whether they underwent a chemical change or not is you take your complete equation and make it a total ionic equation, and then from there you come up with your net ionic equation. So I'm going to walk you through the steps of this particular equation to show you how we came up with it. So I have the same equation written on the board up here. This is a normal single displacement reaction. Your potassium and your lead basically changed who they were partnered with. Right? Lead came and partnered with chromium, and potassium went and partnered with the nitrate. Now, on your slide, I already reported, and I'll add it to this one, what states of matter all these things are. So if you use your solubility table, you'll see that this lead product is the one that's a solid. It's your precipitate in solution. So the net ionic equation is just going to tell you what went into making the solid. Because in reality, your aqueous compounds are just ions in solution. Okay. So how you do it is you take this and you break it up into its ions. If the compound is aqueous, that means the compounds are actually ions in solution, and you want to break up that compound into the ions. So potassium and chromate, that's what that is. You don't need to know that's what it is. You can use your solubility table to get the charge, but this thing is aqueous, and when it's aqueous, it's fallen apart into its ions. So you have a potassium ion, which has a charge of +1, and you have the chromate ion, which has a charge, if you check your table, or you can get it from the balanced formula here, of -2. The other thing you need to report is how many you have, and how many you have can be reported to you in two places. It can be a subscript, or it can be a coefficient. In this case, this 2 is telling me I have 2 potassium ions, and I just have 1 of the chromate. There's no coefficient. Lead nitrate is also aqueous, so you have to break that up into its components. Lead has a charge of +2 based on the fact that this formula has no overall charge. And nitrate always has a charge of -1. In terms of how many there are, there's just 1 lead, and then this 2 tells me there's 2 nitrates. Now, those are my reactants, and they become lead chromate, which is a solid. If it's a solid, then it's not ions anymore. These are bound to one another and they're no longer charged particles, right? They are a compound. So for the total ionic equation, you write them as an entity on their own because they are not ions. But the potassium nitrate is ions because it's aqueous in solution. So potassium is charged of +1. Nitrate has a charge of -1. And then in terms of how many, we have 1 potassium and 1 nitrate in the compound, but you have 2 of that total compound, meaning I end up having 2 potassiums and 2 nitrates in the end. So that's my total ionic equation. It includes every component that was in my double displacement reaction. To get to a net ionic equation, the question you ask yourself is what changed? Okay. What changed is what you report as a net ionic equation. So what I do is I look at my left-hand side of the arrow, which is right here, and I look at my right-hand side of the arrow. And if anything shows up exactly the same on the left and on the right, I cancel it out. So I start at the beginning, 2K plus. I look at my reactant and I look at my product. And if I find 2K plus in my product, which I do, then I cancel out that ion. It does not need to be reported because it didn't change. From start to finish, it's still 2K plus. I check my CrO4. CrO4 minus 2, and I look at my products. Nowhere over here do I have CrO4 minus 2. I have CrO4 in my compound, but it is not the ion. So it can't be canceled because it changed. Pb plus 2, I look at the product. I don't have Pb plus 2 anywhere by itself. Again, it's because it's in the product. That's the solid. And 2NO3 minus 1, I have the exact same thing. 2NO3 minus 1 right here. So that can be canceled. So the final answer in terms of the net ionic equation for this double displacement reaction is CrO4 minus 2 plus Pb plus 2 gives me that PbCrO4 solid. I don't report the things that I crossed out. Let's do one additional practice problem just to make sure you're understanding this. So I already have created a complete and balanced chemical equation for a double displacement reaction. You know it's double because I have 2 compounds. And I've already looked at the solubility table to figure out which ones are soluble and which ones are solid. From this, my next step is to make a total ionic equation, which means any substance that is aqueous means it's in solution. And when it's in solution, the 2 ions have dissociated. So they're by themselves. So if I look at my equation right here, my first substance is aqueous. So I look at my 2 ions. I have this barium ion and I have this nitrate ion. Barium has a charge of +2 if you look at the periodic table, and nitrate always has a charge of -1. The other thing though is with the subscript of 2 here, that means you have 2 nitrates and you need to put that out front. Going to the next substance is also aqueous, so this has dissociated into its ions, which means I have a sodium ion and I have a sulfate ion. Charge on sodium is always +1, charge on sulfate is always 2-. Because of this subscript here, I know I have 2 sodium ions. Moving forward to my next substance, it's a solid, which means it will not dissociate into its ionic components. So I list that as a whole because they are not ions in the solution. That is your precipitate. And then the last one is also aqueous. So I have a sodium ion and a nitrate ion. Sodium's always +1, nitrate's always -1. And because of the coefficient out front, I have 2 of each of those. After I have my total ionic, I want to get my net ionic. And net ionic simply means all I'm reporting is what changed from start to finish. If I have a species, it shows up on the left and on the right. I don't have it show up. So I simply start on the left and work my way down. Barium plus 2, I look at my product. Do I have Ba plus 2 in my product? No, so that is part of my total ionic. And then I move up. 2NO3 with a -1 charge. I have 2NO3 with a -1 charge over there. So that is going to go away because it didn't undergo a chemical change. 2Na plus, I have 2Na plus in the product, so that will go away. SO4, 2 minus, I don't have SO4, 2 minus in the product, so that is part of my net ionic. And then for a final product, I've finished now. I got to go to my reactant side and write anything that's left. And that's the net ionic. On the test, I'll ask you just to take complete and get to net. The total ionic is something that you can do as an intermediate step to make sure you get the problem right. At this point, you should complete the one practice problem that I gave you for homework. Okay? Have a nice night.